OK, so now that we've gone through the code for this example, let's kind of talk about the pros and cons of what we just looked at. And this, again, is the Search with Parallel Streams implementation, which is almost identical syntactically to the Search with Sequential Streams version we had seen before. If you go back and watch that video again, you'll see it's essentially the same. So what are the good things? The good things are that it's really, really, really common. The code is almost identical. In particular, this is what the sequential version looked like for process stream. This is what the code, same identical code looks like for the process stream for the parallel version. Notice the only difference is .stream to .parallel stream. That's the power of streams. And just take a step back for a second. Why is it able to do all this cool stuff? It's able to do all this cool stuff because we're writing our code using functional programming features, and we're focusing on the what, not the how. When you take a look at the assignment 3 that I'll be giving out here in a couple weeks, you'll see that there'll be a sequential version. Actually, you've already seen the sequential version. You used it as the basis for your fork join implementation. And the sequential version of the web crawler is going to just have a loop, and it loops through and it accumulates stuff. Remember we talked about the accumulator anti-pattern? And so what it does is it just goes through and it accumulates things into a single collection, like a list. And the problem with that is that if you want to change it to run in parallel, you have an enormous amount of work to do. You have all this surgery to do to go and create a thread and pass work to the thread and then get the results somehow and join them back together, and it gets out of control. You've also probably seen that you can use the fork join pool, which will give you a speed up. And in fact, if you run your program, once you get your fork join pool implementation running, you can run it in the emulator, and you should be able to see it's a lot faster, if you do it right, than doing the sequential version. You can actually test it out and see how it works. The problem, though, is that there still was a fair amount of work to convert the sequential version to the fork join pool. You had a lot of extra work to do. You have to create this list of fork join tasks, and you have to create objects, and you have to say fork them, and then you have to join them. So there's a lot of extra things you're doing. So the nice thing about the streams approach is once you write it, once you get it to work with a model kind of like this, then the only thing you need to do to convert it to be parallel is to go from that to this. And the reason this works is because we're not focusing anymore on the details of how the parallelism is working. We just are focusing on computations, and then we're letting the framework, the streams framework, do all the heavy lifting to actually process things in parallel. So that's why we can do this magic. It's because we're applying functional programming in the context of a very powerful framework that encapsulates parallelism as an aspect to be configured by calling the right factory method. And as you can see, this little tiny tweak has big improvements. And you can see we end up with a n-fold improvement. Now this is kind of interesting, right? So I've actually got a quad-core laptop. It's not the one I'm running here, but it's my other computer. And it has 32 gig of RAM. And each of the quad cores is hyper-threaded. And if you take a look here, you'll notice that I'm actually getting what appears to be a super linear speed up compared to the sequential version with the parallel version. So here's the sequential version. Here's the parallel version. If you were to multiply this by 4, it would be less than that number, which seems a little weird, right? So I've got 4 cores, but I'm getting more than 4x speed up. How on earth could that be happening? Does anybody happen to know? Yeah. Oh, interesting question. So in this particular case, no. And the reason why the answer is no is because these are all, as we talked about before, they're all compute-bound jobs. So when they run, when you go and do something here, it just runs to completion. There is no blocking. So every time operations are running, they're just going to run to completion. That's in contrast to some other discussions we've had where you might, in particular your assignment that you're working on now, where we're downloading images. So remember, where we're downloading the images, then I/O-bound operations can block. And when images when operations can block, then, as Irfan is saying, there's a win that you get from having more threads so that when one thread is blocked waiting for something to finish, the other threads can go ahead and run. But that's not happening in this case. It's all totally compute bound. So it was a very good guess, but it's not quite the right answer here. How are we ending up with superlinear speed up in the number of cores? If we only have 4 cores, we're getting more than 4x speed up. Work stealing. OK, so it might be work stealing. So another potential is work stealing. So work stealing will help, but the problem with work stealing is you only still have 4 cores, so you're only doing, quote, 4 things, at least in theory. Well, but you're not too far off. So the trick here is that each of these cores is a hyper-threaded core. So the underlying virtual machine actually thinks I have 8 cores. Even though I have 4 cores, because they're hyper-threaded, it thinks that there are 8 of them. And hyper-threading is a technique that was actually added before multi-core. So before we actually had true multi-core, we had something called hyper-threading. And hyper-threading is a technique that Intel processors and most likely AMD processors use too, because they tend to be kind of keeping in league with what Intel does. They're basically ways of potentially being able to get more parallelism, even though they don't actually have physically separate cores. So it's all about trying to be smart about how you schedule the operations that are running. And if you get lucky with a hyper-threaded implementation of a core, in some circumstances, depending on the operations that you're doing, you may get a speed up. It won't be as much of a speed up as you would get if you actually had a fully separate core, because things aren't actually truly running in parallel, but it may be able to run some computations more efficiently. And if you take a look at the Wikipedia page for hyper-threading, it'll explain how hyper-threading works and how it's a bit more speculative than true cores, because they're not really separate processing elements that are running in parallel. And it'll also say that your mileage may vary. Sometimes you see a win, sometimes you don't, sometimes you see a little bit of a win. So this is a good example of hyper-threaded cores giving you a little bit of a win. It's not as much of a win as if we had 8 true cores. If we had 8 true cores, we'd probably expect to see an 8-fold, or roughly an 8-fold improvement. But I have 4 hyper-threaded cores, so we see more than an improvement of 4. We see something between 4 and 8. It's closer to 4 than it is to 8. So that's the reason for that. Another fun thing here. So this computer that I'm actually running here, this is a MacBook Pro that has 16 gig of RAM. For some reason, until very recently, MacBook Pros were limited to 16 gig, whereas the Windows machines of the same sort of equivalent class of processing could have 32 gig. That has changed. The latest version of MacBooks can finally have 32 gig. They also cost an enormous amount of money for that privilege. And you'll also see that this was 2.7 gigahertz quad core. This is 2.9 gigahertz quad core. And if you look carefully here, what you'll see is that because the processing cores are faster, it takes less time to run. So this took about 1,600 milliseconds, whereas that took about 2,000 milliseconds. And you see this took about 373 milliseconds, whereas that took 437 milliseconds. So this machine is faster. But what is also interesting, this is really interesting, we'll talk about this later. You'll notice how on my Lenovo machine, some of the implementations, particularly the ones that use so-called completable futures, which we'll talk about later, they actually ran faster than the simple Parallel Streams version. Whereas on my MacBook Pro, the Parallel Streams version ran faster than the completable futures version. And I think the reason for that is that my Lenovo has a lot more memory than my MacBook Pro. And so it looks to me as though the completable futures work best if there's lots of memory. They can take advantage of memory better. So that's a speculation. I haven't really delved into that in detail, but I think that's the reason. Yes, Irfan. They're not deterministic in the sense that if you were to run the tests, multiple times, you probably wouldn't get 437 each time, but the ordering would be roughly the same. So you might get something different. And the reason for that is that when I run the tests, I warm up the processor cache first. So if you take a look at the code, which is, of course, all available on my GitHub account, you'll see how I start out by doing a test that's meant to get the thread pool warm. And then I run all the tests. And by doing that, because if you recall, once threads are created, they stick around. You want to warm it up first, and then you'll get pretty consistent results. But it's not 100%. You won't get the same values each time, but you're likely to get the same organization of the results. OK, so that's the good part. Parallel streams make things run faster, often. We'll talk in detail later about how that isn't always the case. But for the things we're dealing with here, where we have lots of works of Shakespeare, and we have lots of phrases to search, and there's a fair amount of work to search phrases, search input strings looking for phrases. It's not just a trivial thing like incrementing a count by 1. There really is a win. But there are some downsides. And the main downside is just because we did minuscule changes to the code doesn't always mean it's the best thing to do. So you'll notice that there were other implementations that actually ran better than the Parallel Streams one. Now, the big question you have to ask yourself is, does it matter, right? If somebody is going to, pay you to write a program and you want it to work well, and they say write it in Parallel Streams, and you make it work, and it's n times faster, and their requirements are satisfied, you can declare victory and take your consulting income and go on and look for the next piece of work, right? You can say, I made it work just fine. There are some environments, of course, where every nanosecond matters. So in those environments, you really want to stretch and do even better. And so that's, of course, what we'll talk about in the rest of the course. So there are other strategies that run even more efficiently than just the naive version. And that, of course, requires you to learn about things like parallel splitterators, that requires you to learn about things like completable futures. And you can see there's even different versions of completable futures that work in different ways. So the key thing to remember, and this is sort of along the lines of what Irfan was just asking about, your mileage may vary. As they always say when you go to buy a new car and it says, EPA estimated mileage is, this amount in the city, this amount on the highway. But your mileage may vary. And if you drive a Volkswagen that had diesel fuel, your mileage will definitely vary, right? Because they had all these little hacks they put in the software that would trick the tests to think your mileage was higher because they would behave differently when they were being tested than when they weren't. Very sneaky and subversive. Also got them in like billions of dollars worth of fines. In this context, unlike Volkswagen diesels, there's no substitute for benchmarking and experimentation. So if somebody says, how well does your code run, you can estimate it'll probably run faster if I use a parallel version, but you need to measure it to make sure. And a little bit later in the course, we'll talk in much more detail about when you should be using stuff that's parallel and when you shouldn't. In a nutshell, the thing to remember, and I'll go into this in more detail, but the Cliff Notes version of all this is the more items that you're processing for the input and the more processing you do per item in the input, right? If you take the number of items, let's call that n, and let's call the number of processing operations per item q for quantity or quality or quantization or whatever. N times q. If n times q is large, then you're likely to get a speed up from parallelization. If n times q is small, you probably won't. And of course, the question is, what's the break-even point? And there really is no easy answer because it depends on hardware, it depends on software, it depends on the data, and so on and so forth. But the thing to keep in mind is if you have lots of items and each item is processed a lot and they don't have many dependencies or any dependencies, then parallelism will make you make your program much, much faster. Yes? What does benchmarking mean? So when you're trying to think of a good, well, I'll give you the computer example, and we'll see if we can find an everyday example. So benchmarking is what you do when you run different tests. You run a benchmark. You say, what runs faster? Sequential streams, sequential loops, parallel streams, completable futures? How do we know which one's better? You have a benchmark. So you check to see which one runs better under essentially the same conditions. Think about this, right? How do you know What's your favorite automobile? What's your favorite car? Ferrari, Lamborghini, Corvette? Okay, well, we'll pick one for you. So let's say that your favorite car is a Ferrari. And so you're arguing with your friend whose favorite car is a Maserati, right? We'll keep it in fast Italian sports cars for the sake of argument. Which one's faster? How do we know? You'd have a benchmark, right? You'd put the cars out on the track with the same conditions, and they have to go the same distance. They both start at the same time, and you say, run, right? And so you run them and you benchmark them, and you see which one runs better. What's the question? So I think if I understand the question is, how do you ensure that the benchmarks you're doing are consistent, right? So there's lots of different ways to do that. First, it helps to understand like what affects performance. So in the particular case here, what affects performance mostly is two things. First of all, does everybody start with the same number of worker threads in the fork join pool, and are they already warm and up and running and already created? That's the first thing, right? Because it wouldn't be fair to run one thing where the worker pool was uninitialized initially, so they had to pay the cost of creating the thread pool. That would be unfair, and then somebody else can take advantage of that. So you have to make sure that they have the same conditions. It would be kind of like benchmarking the two cars, but one car was in a wet track, the other car was in a dry track, right? That wouldn't be fair. You wouldn't be comparing apples to apples. You'd be comparing apples to oranges. So making sure that they all have the same things properly initialized, that's very important. And then another thing that matters a lot in Java programs is making sure that you're getting the same responsiveness with respect to memory management. So the big thing with Java, as you probably know, is that memory is allocated dynamically. And when you run out of memory, a garbage collector runs. And if you were doing a test and one test, let's say, I don't know, Parallel Streams, that never garbage collected while the test was running. But let's say that, I don't know, RX Java inputs suddenly got a garbage collection in the middle of it. Oh my gosh, right? Now you're comparing apples to oranges because one is getting a garbage collection. Maybe it happens to be that, depending on the order in which you run the test, you'll run out of memory halfway through one of the tests, and then you have to pay the cost of garbage collection. So the way that the test benchmark works, and you're welcome to take a look at it to understand how it works, is it makes sure to do a garbage collection between every run. So after, let's say we start with this one, we run this one first, and then we garbage collect. You can automatically trigger garbage collection in Java. Then we run this one. Well, this should start out with a heap that's all fully available and ready to go. So it also helps to have 64 gig of memory. You don't run out of memory very much, but it probably never garbage collects, actually. So as long as we're making sure that we're using memory in fair and consistent ways, then you should be fine. If you're really super duper duper obsessed with this, you could write a program that would try every permutation of the input tests. You could run this one first, and then next time you'd run that one first, and then this next time you'd run this time. You could do, n factorial number of combinations to run them all. I suspect you'd probably see more or less the same results, but if you were really obsessed, you could do that. I was not that obsessed, but I also ran the test long enough to see that the environment was the same. So the key point here is you want to make sure that you have a consistent environment for doing the testing, and you account for the factors that influence variation in performance, which in this case would be, are your threads in your worker thread pool warm? And do they all have a free store that's initialized to be full when you start, so you don't end up triggering garbage collection halfway through? I will show you how to overcome this problem where you just sort of, don't take full advantage of parallelism. Probably next week we'll go over this. So we'll talk about search with parallel iterator. This is yet another variant, and this variant is super cool because it's going to do one more degree of parallelization. So what happens here is in the Parallel Streams version, which is this guy, we run all the input strings in parallel, and for each input string, we run the search phrases in parallel. So we get parallelism in 2 dimensions. And as you can see, that performs pretty well. This version, which we'll look at later, we're going to do one more additional step of parallelization. What we're going to do is when we search a given phrase in a given string, we're going to use a parallel split iterator. So we're actually going to take the string and we're going to split the string up. Remember, the string corresponds to a work of Shakespeare. So we're going to take all the text in the work of Shakespeare and we're going to split that up into multiple chunks. And then they will search a given phrase in all of those multiple chunks of the work of Shakespeare in parallel. So it's even more parallelism. And as you can see, that actually does give us a win. So when we run the fully parallelized version, where we're parallelizing the input strings, the phrases, and then searching for phrases within an input string, when we parallelize it out the wazoo, which is a idiomatic phrase, taking it to the max, or whatever is the right translation for that, we'll see that we get things to run even faster. Now, as it turns out, that requires a fair amount of work, because we have to make sure that the parallel split iterator code that we write will search for phrases in a given input string by chopping up that input string into chunks in such a way that each chunk doesn't accidentally cause the phrase to be split between chunks, which would mean if you were looking for a phrase, it would be in there, but you wouldn't find it because of the way you broke the string up into chunks. And so we're going to write a really, really cool phrase match split iterator that's a parallel phrase match split iterator that's going to make sure it preserves the chunk boundaries so that phrases are guaranteed to be found, if they exist, in the chunk in the right place. Yeah? Does this mean for each task, when you say task, what do you mean? Okay, so if I understand your question, for the version that we're going to talk about later when we get to this, we're going to use a split iterator, and the split iterator will take the input string we're searching, like Hamlet, and it's going to look at all the phrases, and for each phrase, which will run in parallel, we're going to split the text of Hamlet up into chunks, and each of those multiple chunks will then become a task that will be run in a thread in the fork join pool, so we don't know which one it is. It's just some thread that's available. That chunk will then search for the phrase in parallel with that same phrase in another chunk that's not the same chunk. So we'll end up with, let's say we break Hamlet into 8 chunks. For any given phrase, we will search each of those chunks in parallel. And of course, under the hood, this is implemented with tasks in the fork join task model you guys have been playing with. And each of those tasks will be mapped to a worker thread in the fork join pool. But all of that mechanism of the fork join pool is, of course, hidden from you in this model. You don't know, you don't care that that's going on. But it is going on. So it makes it run faster. OK, any other questions about that? So that's the end of the Search with Parallel Streams example. We will revisit this example later next week, after we've had a chance to talk more about how things kind of work under the hood.